So we're going to close this. Okay, and then I guess I need a pen. That's a little bit small, but we'll see. Do this. Okay, so we have this table. I'm going to write over here. So we are trying to fill in the symbol. Try not to. And then we have to decide if it's an ion or not, and what type of ion. Oops, I don't know. I put it tall. And then protons, and electrons. Okay, so the first one, what should the symbol be for this thing? What's our atomic symbol?
Bromine.
Good, bromine. Br. Okay, and then is this going to? Oh, we have neutral. This is neutral. Okay, I don't know that. How many protons?
The same as electrons.
Good, 35, 35. Good. Okay, how about the next one? What kind of ion is N2 minus?
It's an ion plus 2 electrons.
Good. And more electrons. Good. So how many protons does it have if it's nitrogen?
7 protons.
So 7 protons. Always, always, always. This is the atomic symbol, or the number, atomic number. And then how many electrons?
9 electrons.
Good. Good. Okay. And the last box. What's the symbol here if it has 13 protons?
It is aluminum.
Good.
Aluminum.
Good. And then what else do we need here?
That's a cation plus more quantum.
Good. So we need a plus symbol. So this says 13, this says 12. And then it's a cation. Good. Okay, so this is pretty straightforward. This is something that sometimes will trick people on the final just because it's been so long. And sometimes they flip. If it's negative, we need more electrons. Okay? If it's positive, we need more protons. All right, questions on that? Okay, good. Seems like we did pretty good on that. Okay, let's go back to look at our schedule really quick. Just make sure. Oh. Where did I close it? I closed my schedule. Let me. Do a new one. Oh, they're over here. That's what's going on. That's confusing. All right, let's look at our schedule really quick. So today we're going to start chapter 6. So we'll work on this. We're going to take 3 days in class for chapter 6. So I will work on a new schedule for December, but we're in the last week of November. So we'll work on chapter 6 on Wednesday, and then we'll do lab 3 on Friday. So yes, the pre-lab will be due on Friday. We can talk about the pre-lab next time in class, okay? All right, questions for me on our schedule. So we'll take 3 days for lab, or chapter 6. Then we'll do a review day, and then we'll do a test. Okay, all right. So let's go ahead, let me pull up my ALEX. These are the ALEX topics that we need to cover. We're gonna kind of go through and do a similar thing we're gonna do. Mostly just do the ALEX topics with a few notes. So let me pull up my ALEX. If you want to also pull up your ALEX, that will work. And I would do it where I will drop it. We have a section to do the knowledge check. Sure. Yeah. Do you want to do that? How long do you want for your knowledge check? 15 minutes. Okay, let's start with that. Okay, I will put up a timer. We'll see where we are in 15 minutes. Okay, we'll see where we are in 15 minutes. Yes, so I don't have it set up yet. I probably won't have it set up on Thursday. So you can come on Thursday. Okay. So if you want to just come during first, or you can come after, like that week after. What race are you doing? Are you running? How long? It's like a 3 mile race. And you drink with, you want to drink inside? Oh, is it? And just remind me when you got when you want to do that. Okay. Yes. So you can come in like after school. Okay.
This is more heavy. That's more closer. So it's in 6 page after, right?
So we don't have to let tomorrow or
last.
yeah, you should come on Thursday.
So and this last.
Yes, is that what you
VR.
Okay.
So I go at VR.
Okay, yeah.
Or VR. You're welcome.
Avery. Okay, so for this question, we need to know some conversion factors. So this is something that is in ALEX. We need to know how to convert between kilocalories and kilojoules. Mouse. So let's see. If I look in ALEX somewhere, oh, can't find it right now. There it goes. So if I look in the data, yeah, and I go to unit conversions for non-SI units, so the fourth one down, if I scroll all the way to the bottom, oops, almost all the way to the bottom. If I'm looking at calorie, we abbreviate that with CAL, and this is my conversion factor. So you can find this in ALEX. I would write this on my note card just because I know I'm going to use this on the chapter 6 test, so I would put this in my notes. I'd write it on my note card. So 1 calorie is the same as 4.184 joules. Okay, and then I'm going to do something tricky. I'm going to, it's not really that tricky. I'm just going to put a K in front of both of these. So I'm going to times both sides by 1,000. So if I do it on both sides, it's fine. So if I say 1 kilocalorie is the same as 4.184 kilojoules. So by putting this K here, I'm just multiplying both sides by 1,000, okay? And this is gonna be more useful to me on this Alex topic, okay? So calories is a unit that we use a lot in chemistry, or in nutrition. So if you look at the back of the label, it's in calories, but that's in calories with a capital C. So the capital C calories is the same as 1 kilocalorie. So that's really 1 calorie on the back of your food label is 1,000 calories, little calories, okay? And then the science calorie, this definition, this little calorie, is just the energy it takes to heat up. I think it's 1 gram of water, 1 degree Celsius. So that's the definition that we've created for calorie, okay? And we use it a lot, and that's why we're using it in Alex. Okay, question so far? We're good? Okay, let's go over this topic then. So this is just a conversion question, so not too tricky, just converting between these. So this is how it will also be on the test. So the first one says a tablespoon of corn oil is this many calories. We need to convert it to kilocalories. So this part is pretty straightforward. We are just going to go from calories to kilocalories, so we're just going to divide by 1,000. So let me write this down. So we have 1.4 times 10 to the 4 calories. Okay. I need to go to kilocalories. So I'm going to put calories on the top, kilocalories on top, so that I end up with kilocalories. And I put calories on the bottom. And I know that I have 1,000 calories for 1 kilocalorie. So that might be another one that I write down. So 1 kilocalorie is the same as 1,000 calories. Or out of space there. Oops. Okay. So if I'm taking this number divided by 1,000, I'm just going to subtract 3 from the exponent. Okay. Or I can type it in my Alex calculator. Either way. So maybe we can do that. Oh, it's my Alex calculator. Alex disappeared. There we go. So 1.4. 1.4. Oh! Now, 1.4 times 10 to the 4. I'm going to divide this by 1,000. Oops. I'm going to jump. How do I do this? Oh, there we go. Divide by 1,000. So my exponent will just go down by 4. So, by 3, excuse me. Okay, or just 14. Okay, when I put this in here, I need to use this number to tell me sig figs. So how many sig figs are here?
3.
So how many do I need here?
3.
Okay, so what should my number be? I only have 14. 0.0, perfect. Good. I don't need to put a unit because the unit's labeled in the table above. All right, so then I need to take my number, my 14 kilocalories, and we're just going to do another unit conversion. So we take 14 kilocalories, and I need to convert this. My box is telling me it needs to go into kilojoules. So this is the one I'm going to use. So kilojoules is going to go on the top. That's what I need to end up with. I need to cancel out kilocalories. That's going to go on the bottom. And my unit conversion says 1 kilocalorie for 4.184 kilojoules. So I'm just going to type that in. So 14 times 4.184. Okay. And then I'm going to type it in here. How many sig figs?
3.
Okay, good. So 58 points. I need to round that up to 6. Perfect. Good. Okay. All right. Then this one we're going backwards. So here we divide by 1,000. If we're going to go backwards, we need to multiply by 1,000.
So this be
Yes. So I'm going to do 45 times 1,000. And remember, I can make my Alex calculator, put this in scientific notation for me and copy paste. Okay, remember I need a match sig figs. So I need to put a 0. 4.5, that's only 2. Let's add a 0 to get 3. Okay. All right, and then we're gonna go from 45. That's in kilocalories. So we're gonna do the same thing we did there. 45. Oh, I'm just gonna bump it up a little bit. 45 millilocalories. I do the same thing that we did just here. Oops, that is 4.184 kilojoules for 1 kilocalorie. Kilocalories cancel, we'll end up with kilojoules. And then, I don't know that, I'm gonna type it in. So, go to my calculator, 45 times 4.184. I don't need that in, let's see, let's go back to decimal. So then I need 3 significant digits. I'm just gonna do 188. I'm gonna put a decimal. So I think you need a decimal, so watch out for that. Okay, what was that? That was a chocolate chip cookie that has 188 kilojoules. Okay, and then the last one, I think it's easier to go from kilojoules to kilocalories and then kilocalories to calories. So that's what I'm gonna do. So just another unit conversion. I'm gonna put it here. So we are starting with 523 kilojoules. Oops. I need to end up with kilocalories. So I need my unit conversion that has kilocalories. I'm going to cancel out kilojoules, so that goes on the bottom. So kilojoules, 4.184 kilojoules for every 1 kilocalorie. So kilojoules cancels out, and then we'll do 523 divided by 4.184. Okay, so then I'm going to type that into here. 523 divided by 4.184. Okay, and I need, this tells me I need 3 significant digits. So this box, I need 3 significant digits. 125, I'm going to put a decimal. And then from this box to this box, I need to multiply by 1,000. I'm going from kilocalories to calories. Let's write that one out just for fun. So 125 kilocalories, we need to end up with calories. So calories needs to go on the top. We have 1,000 calories for 1 kilocalorie, which is also representing 1,000. So kilocalories cancels out. So then we would end up with 125 with 3 zeros, or 1.25 times 10 to the, I think I counted 5, 1, 2, 3, 4, 5. And I need 3 significant digits. Let's see, 1.25 times 10 to the 5. Okay, before I move on, I just want to show you all of these. I think this is usual. All of them have 3 significant digits. So that's one way to check. At the end, look at all of your numbers. Make sure they all have 3 significant digits. Make sure you have decimals at the end of, it just doesn't have a 0 at the end or a decimal. And then the other thing to look at is like, these ones all have exponents. If I end up with an exponent over here, maybe that's wrong. So that's another way to check, okay? If you have a times 10 to the 5, that's probably wrong over here. These ones are bigger numbers. These ones are like little numbers. These are medium numbers. Okay, so that's another pattern to watch for. That's just a quick way to check. Okay. All right, let me check, make sure I did it right. Okay, questions on this type of question? Do you want to go over another one of these? We're good? Okay. All right, let's go to the next topic. Oh, sorry, you get that? Okay. All right. The next one is we're going to go to calculating a heat of reaction from molar enthalpy. Okay, before we do this, we need to look at a few notes. Let me find my notes. I put my notes in here. Let's see if I can read my notes. Let me move my notes over here really quickly. Hold them up. So there's just a few things that are important from these notes. So I wouldn't write all this down. This is just like an overview. So just stay with me for a minute. Again, I wouldn't write all these things down. Oh, why is it so big? I need to go smaller. What's that? There you go. Okay, so chapter 6 is energy and chemistry. So if you took physics, you might have used kilojoules or calories as a unit before. Did anyone take physics? Okay, someone else did, that's okay. So physics, we use joules a lot. In chemistry, this chemistry class, we're going to use kilocalories and calories more. So when we break a bond, we have to put energy in. So when I think about this, I just think about if I have a pencil and I want to break a pencil, I'm going to put energy in. Okay, energy goes into the reaction to break bonds. When I make a bond, energy comes out of that reaction. Okay, so notice these are the same reactions. So if I'm breaking the bond or making this chlorine-chlorine bond, it's the same value. But one, this bottom one, I'm getting the energy out, so this reaction would feel warm. And this one, the energy I would have to put in. So think about, this would be like a cold pack, the energy would be leaving the surroundings. This one, the energy is coming out of the surroundings, it would feel warm. Okay. So this is what I would write down. If it's an endothermic reaction, energy is absorbed, and this heat of reaction that we're going to start talking about is positive, okay? When energy is released, that is an exothermic reaction, and delta H is negative. This is something that I would put on my note card so that I don't get it confused on the test. Sometimes people will flip this, and then they get a whole bunch of questions wrong because it's flipped in their head. So if you write it down on your note card, then you'll have it down. So this is something that we can measure. So that's pretty interesting. We can measure how much energy is coming out or going into a reaction, a chemical reaction. Okay, let's practice really quick. I have some extra slides in here. All right, so the top one, delta H is positive or negative? Delta H is negative. So is this exothermic or endothermic?
Exothermic.
Exothermic, negative. Good. How about this one?
That's a positive.
Positive number,
Endothermic.
endothermic. That's all you have to look at. How about this one?
Negative.
Negative, exothermic.
Exothermic. Negative.
Negative, exothermic. Okay, so you just need to look at the sign on the delta H. Is it negative? Then that's exothermic. If it's positive, it's endothermic. And that's why it's so important that you know that. So either I would write it on my note card for the test. Okay, let's go to Alex and do a topic that is related to this. Calculating the heat of reaction from molar reaction enthalpy and the mass of the reactant. Okay, so when we're looking at this, the first thing that we need to do is look at the delta H. So this one says negative. So the first one, exothermic. Negative, exothermic. That means energy is exiting. We would feel that as heat. Okay? All right, so suppose some of this reacts. Will any heat be released or absorbed? This one is always yes. We just have to decide if it's yes absorbed or yes released. Don't pick no on this question ever. Okay. All right. So is it yes absorbed or yes released if it's exothermic? Yes released. Good.
Oh, yeah.
So exothermic released. Yes. Endothermic would be absorbed. Always click yes. Okay. All right. So then this is the tricky part. So we need to figure out how to do this one. So we need to also remember some of chapter 5 for this question. So let me pull up some paper. Is this too small or is that working okay?
That's fine.
That's working okay. Okay. If I put it on my board, then people miss it. They don't see it. They can't see my whiteboard when I'm writing on the whiteboard. Okay, let's move that. All right, so we have this value. We have 57.3 grams of, do you guys know what CH4 is? So it's methane. CH4 is methane. Okay, and then we need to figure out if this much methane reacts, how much energy is released. Well, this chemical reaction tells me if I have methane and I react it with oxygen gas, then I'll get carbon dioxide and water. And if this reaction happens for 1 mole of methane, there's just a 1 here, that gives me 882 kilojoules of energy for every 1 mole of methane. So the first thing that we have to do here is we have to figure out how many moles is this. Okay. So do you remember from chapter 5, if we have grams, how do we get moles? So Avogadro is related to moles. We're going to use the molar mass. Does that sound familiar? Yeah. So we need to get how many grams of methane for how many 1 mole of methane. Remember this? So we need to add up. This is the number. This is our molar mass. We need to add up carbon plus hydrogen times 4. Hydrogen, 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 hydrogen. So our molar mass. Remember doing that? So let's write that. Molar mass of methane. So I'm going to use my Alex calculator. I just need to slide this over. Oh, not that way. You just slide this one over. So I need to figure out how many moles or how many grams of methane before I have a mole. So let me find I need 1 carbon. And then I need 4 hydrogens. So that gives me 16.04096. So that's how many grams for 1 mole of methane. Okay, do you remember doing that in chapter 5? Oh, thank you. Okay, so if we have our number in grams, we need to divide by the molar mass. So 57.3 times 1 divided by, I'm going to change this number to 16.04096. Okay, question so far. Reading all right?
So it's that number divided by the molar mass.
Yes, this number divide by the molar mass. Yes. So you can write that down. Yep. So like for this question, we're going to take our mass and then divide by the molar mass. And you have to calculate the molar mass.
So if there
That will give us the moles.
is there always just the one of it? Like there's just one methane?
No.
Okay.
1 methane. No. You need to look at the chemical equation. Yes. Yeah. Good question. Okay, so let's do that. Let's do our number divided by our molar mass. So 57.3. Right? Is that right? Okay, divide by our molar mass. Oh, come here, molar mass. Okay, so now we just found that we have how many moles? We have 3.5 7. So Alex recommends that we keep 2 beyond the number of sig figs. So this has 3 significant digits. This is an intermediate number. I'm not going to type this in anywhere. I'm going to keep 5 significant digits just to make sure that it doesn't mess up my answer at the end. Okay, that's just, Alex recommends that. Or you can just leave it in your calculator. That's probably what we'll do. Okay, this is moles. Let me write it down here. This is, so we just found we have 3.5721 moles of methane. Well, this chemical equation says that if we have 1 mole of methane, we get this many kilojoules. So I need to figure out how many are released if I have 3.57 moles. So I'm just going to multiply this. So this says I have negative 882 kilojoules for every 1 mole of methane. Okay. And Ian pointed out that you do need to watch. This one has a 1, but if I was given how many grams of oxygen, this is 2 moles. So I have 882 for every 2 moles of oxygen. So I would just put, if there was a number, if there was like a 6 in front of the methane, I would just put the 6 in my ratio. Does that make sense? We would do it right now, but we don't have a 6. We just have a 1. Yeah, good question. Okay, so I'm going to times that. So if I have 3.5721 moles, how much energy comes out of there? And then times it by 882 kilojoules per mole. Okay, and then I have this number. How many sig figs can I have? 3. So this has 3, this has 3. My number can only have 3. So this has a lot. Let me put it in scientific notation. I'm going to keep the first 3. I'll just copy paste. One, 2, 3 sig figs. Okay. Questions on that? So this one's exothermic. I'm going to keep the negative sign. That makes sense to me. Someone in the other class said that you can put it in both ways. So you can, if you just always put this in as a positive number, it will always accept it as positive. I think it makes sense to me that it's exothermic, so I'm going to put a negative. Okay, questions on that one? Do you want to do another one of those? Okay, let's do another one. Can I move to the next screen? Do we need this one? Okay. All right, is this still working okay, the paper? Okay. All right. There's a light that's over here. All right. So this one says we have, this is mercury oxide, and then it splits into mercury and oxygen gas. Okay, first, is this endothermic or exothermic? Endothermic, good. And how do you know that? Good. All I have to do is look here. This is positive, that's endothermic. And then suppose this much reacts. Will any be released or absorbed? Yes, absorbed. Good. Okay. So never put no on that one. Okay, so then we just start with this number, 41.8. This is grams of mercury oxide. We need this in moles. So what are we going to do? What's our first step?
Moles on top.
Yep, we need 1 mole for how many? We need to figure out moles of mercury oxide.
See the molar mass.
Good, so we need the molar mass. So we need to figure that out.
moles in the top. Because
For the molar mass, it's only per 1. Yep. So let's calculate that. I'm going to use the Alex calculator. So I need 1 mercury, and I need 1 oxygen. That's how much 1 mole of mercury oxide weighs. So 216.5914. Okay. Yeah, we can just keep 5 if we wanted to. So I'm going to take my number, divide by the molar mass. So 41.8 divide by my molar mass. Oops, oh, I don't know why it doesn't do that. Divide by this number. So we just calculated how many moles of mercury oxide we have. So we just have a small amount. We don't have a lot. 0.19299, something like that. This is moles of mercury oxide. Okay, so then let me take that number, 0.019299 moles of mercury oxide, and we need to figure out how many kilojoules is released or absorbed. So because it's endothermic, it's absorbed. And this is saying for every 2 moles of mercury oxide, we get out 182 kilojoules. So I'm going to say for every 2 moles of mercury oxide, and I'm going to put that on the bottom so it cancels, I get out 180, or I have to put in 182 kilojoules. So I end up with kilojoules. So moles of mercury oxide cancels out. So this one I'll have to take the moles of mercury oxide I have multiplied by this ratio. Times by 182 divided by 2. Okay, and then we get out this number, 17.562. This number has 3 significant digits. This one also has 3. We use both of those. So we can only keep 3 significant digits. So I'm going to round this to 17.6 kilojoules. Okay, weird thought. Questions on that? Okay. Okay, how do you feel about this one? Do you think you're good on this one? Okay, I would like to cover one more topic. I know we've got 10 minutes, but is that okay? You had your work time at the beginning, so we'll do one more topic. Okay. Okay. The last one I want to talk about is, and it's pretty straightforward, interpreting a reaction energy diagram. Okay, so we have to figure out what this means. So let me write a few notes on this paper. So we just talked about endothermic, and we talked about exothermic reactions. We can look at these using this type of graph, which is called an energy diagram, or I also call them a reaction coordinate diagram. Okay, so we have something like this. On the y-axis, we have energy. And then on the x-axis, this is the reaction progress. Or they're talking about, this is called the reaction coordinate, either way. So reaction coordinate diagram. So if it's endothermic, that means we had to put energy into the reaction. So this first level is the reactants, where our reaction starts. And where our reaction ends is the products. I think I forgot to put it. So this is where we start, this is where we end. This is called the transition state. So every reaction, to get it to go to the products, we have to put energy in to get it to transition to our products. Okay? And the difference between where our reactions start and this transition state is called our activation energy. Or energy barrier. So this is the amount of energy we have to put into the reaction before we can fall over this cliff and get our products. Okay? And this is how chemists are modeling how reactions progress. Okay? We can do lots of predictions with these types of reactions, or these types of graphs. Okay, so if we're looking at an endothermic reaction, the products are higher in energy than our reactants. Okay, exo is just opposite. So our reactants are maybe here. We still have an activation energy. We still have to go through the transition state, and then our products over here. And our reactants. And then our transition state. and then our activation energy, or activation barrier, we also call it that. So I'm just going to draw an arrow. Okay, so now hopefully we have enough information to answer these types of questions. So we have our energy diagram. This is something I might also put on my note card, because if you get those flipped, then you'll miss a few of these questions. So, let's jump down to this one. Is this one exothermic or endothermic?
Which one? This one ended because more energy in the end.
Good, perfect. More energy at the end, endothermic. Good, good. Okay, so then the heat of reaction, so that is this delta H. Delta H is our heat of reaction. To find the heat of reaction, we always take our products and we subtract our reactants. That's called our heat of reaction. All right, so if we look at this diagram, these are our products. So that looks to me like 250. And this one's 100.
So 150.
So 150. And this one, it matters the sign. Endothermic has to be positive. And I'm gonna, this one, you keep as many decimal places as are on the graph. So there's none, so I don't need a decimal. I learned that last time. Okay. Can you determine the activation energy? So activation energy, you take this transition state and you subtract the reactants. So we can write that. I'm going to speed this up a little bit. This is our activation energy. And activation energy is always positive. Okay, so watch out for that. So we're going to take our transition state. And we subtract, I ran out of space, we subtract our reactants. So it's just that gap between the topmost of our graph and where we started. Okay, so this one, the transition state is at 400, the reactants are at 100, so what is our activation energy? Good, so always put yes. Yes, I can calculate it. Don't put no, that means it's not looking at the graph. So yes, we can calculate it. Then, this is the next part. Can you determine the activation energy of the reverse reaction? So this is just, you imagine, you take your graph and you flip it. And you say, oh, now I'm starting here. I'm going to have to go over the activation energy, the barrier, and then get to my product. So this is my reactants, this is my products. So the activation energy for that is take my activation, my transition state, and subtract my new reactants. So this is my transition state 400, and my activation, I'm looking for the activation energy, my reactants. So what would that be? 400 minus 250. 150, yep, good. Yes, 150.
So it's always like yes.
It's always yes, these ones are always yes, don't put no. Okay, questions on that? Let me check. Okay, do you want to do another one of these? Are you good on that? Okay. All right, we're gonna stop there. We have 4 minutes left.